So I'm just starting the webinar now, Walter, and handing over to you.
Okay, so good morning, good afternoon, good evening, everyone. Depends on where you are. So welcome to the EBIPSA education webinar. This is a sixth webinar for the BOPTEST series. And today we are very happy to have two presenters, Huayu Jiang and Jaap Neven, to share their work. So before we start, I would like to introduce our EBIPSA education committee. So basically, the purpose of this committee is listed here. And also, we would like to remind you that we will take questions at the end of both of these two presentations. So at the end, and when you have questions, please type in your questions to the Q&A box, and we will read it aloud and invite the speakers to share their answers. So with that, we will start today's webinar, and we will have Huayu Jiang present first. And now, Huayu, the floor is yours.
Okay. So can I start now?
Yes, please.
Okay. Hello, everyone. I'm Huayu Jiang, and I'm a supervisor is Professor Wang, and I'm from the Hong Kong University of Science and Technology. Today, my topic is Tiny-AMPC, hardware-aware compression of MLP controllers for mixed-integer MPC. So this talk will focus on how to use BOPTEST to develop and evaluate compact controller for fixed frequency AC and how to further deploy it on the edge equipment. Here is the outline. So let's start with the background. Fixed frequency AC still dominates in the US residential market, which accounting for more than 80%. So it presents a massive potential for advanced control strategies. But it leads to a problem because if you want to control the fixed frequency AC, that means the control signal must be binary on-off control. So that leads to the NP part optimization problem. So this leads to the first gap. Even though mixed integer MPC can be used to improve performance of fixed frequency AC, MIMPC require high performance equipment to solve complex mixed integer problems. And solving MIP is often computational prohibitive for low-cost embedded hardware. So what we want to do is to utilize approximate MPC to use neural network to imitate the contraction of teacher MIMPC without solving MIP. Even though approximate MPC is good, but it still requires some non-negligible memory to store the full model. So you can see if most the MCU deployed on the residential fixed frequency AC is very resource limited, especially compared with high performance equipment like cloud server. So if you want to deploy the AMPC on the MCU, you need hardware-aware algorithms to shrink the size of model and accelerate the operation speed simultaneously. In this research, we use post-training quantization-aware training, and pruning to do this. After model compression, the model's accuracy may be compromised. So in this research, we will explore different compression ratios to identify one that both reduce model size and ensure good control performance. So based on that, here is the overall workflow. At first, we developed a reference for MPC, which is a fine-tuned mixed integer MPC. And then we use this for MPC to generalize some training data set. And then we use this data set to develop some MLP. And then we use model compression algorithm to compress the several MLP. And then we find the best one which reach the best trade-off between control performance and model size, and then develop it on the hardware. So let's start with the system setup and test bed. In this research, I use BOPTEST. Specifically, I use the test case, which is called best test hydronic heat pump, and I test the teacher MPC and AMPC under the peak heat day and typical heat day. For the teacher MPC, the thermodynamic model I use is 1R1C model, and because our target is to control the fixed frequency AC, so we need to know the maximum heat pump electrical power and maximum thermal power. For this test case, the maximum power is 3.4 kilowatts, and the thermal power is 10.6 kilowatts. Because it is fixed frequency AC, so only of actuation for both AMPC and teacher MPC, the control step is set to 10 minutes, and the control and the prediction horizon is set to 6 minutes. And all of the forecast list here will be sent to the both MPC. So let me briefly introduce the full MPC. Here we use a self-constrained MPC. You need to pay attention to the objective function. It includes 3 parts: energy cost, thermal discomfort, and time switching on off. The first 2 terms is easy to understand, but why we set the third term? Because the 2 frequency on-off behavior may be harmful to the equipment and occupant comfort. And then these are the constraints. So we use this for MPC to generate some training data set and use the training data set to treat these 3 sizes of MLP. The first small one, which includes 2 layers, the medium, which includes 3 layers, and the larger one, which includes 5 layers. And then for the hidden layer, we use ReLU, and we use sigmoid for the output layer. And here, all of the input feature can be divided into 3 parts. First, the first part, previous control action. The second part, current system state, and the third part, future disturbances. So altogether, you can see 184 features will be input to each MLP. And all of the feature will be processed by the MLP and then get 1 continuous control signal from 0 to 1. And this continuous control signal will be converted by the threshold into binary of control signal. And then before I introduce why the compression algorithm is very useful and efficient, let me briefly introduce the data type. In the machine learning models, almost all of the weights and bias are stored in the FP32. That means 4 bytes. If you want to store 1 number, 4 bytes are required. So if we can convert the FP32 number into int 8 number, that means the store size will decrease a lot, because you can see only 1 byte are required to store 1 int 8 number. So that's how the quantization algorithm do. So at first, we use the most simplest quantization algorithm, which is called post-training quantization, or PTQ. Here, the diagram shows how the post-training quantization works. It's the simplest one, but it just simple maps the FP32 number into the low precision number. So you can imagine the control performance will degrade a lot. So to address that, we also tried quantization aware training, or QAT. So this algorithm can let the MLP adapt to the quantization noise during the additional training process. So the control performance will improve a lot compared to the post-training quantization. But you can see here is additional complex training process. And then the third algorithm is called pruning. Here the diagram shows how it works. It's just you use scissors to cut off the branches on the tree. So at here it just eliminate the less important neuron from the MLP. So and here, if you want to use the pruning algorithm, here the pruning granularity criteria and ratio need to be set. First, we use neuron level pruning. That means you need to remove this neuron and all input and output weights connected to it. And then the criteria in this research, we just said, I think the weights with larger absolute weights are more important than other weights. And third, the pruning ratio. The pruning ratio means the proportion of the neurons that are eliminated. And because in the research, we want to find which compression ratio is can show the best trade-off. So we tested it from 10% to 90%. And then after the pruning, here is additional fine-tuning required to improve the performance of the model. And some research finds that if you combine the pruning with the quantization, the model's performance will be better. So here we also combine the pruning with the quantization. Now it is this slide shows the evaluation metrics. It can be divided into two parts. First, the system overhead. In this part, we use flash and RAM usage to evaluate the system overhead. And then secondly, the control KPI, we use the operation cost, thermal discomfort, and the switch count to evaluate the control performance. And we design a simple hardware in-loop system for testing. For the hardware side, we select the STM32H753. You can see the flash is only 2 megabyte and the RAM is only 1 megabyte, so it's very resource limited. And for the software side, it is a PC on which the BOP test is running. So for the system, if you want to push one control step, at first the BOP test will send the forecast and current state through the serial port to the STM32 controller. And then the AMPC deployed on this controller will process the information and then get one control signal and then send back to the PC. So you can just imagine that the STM32 just like a real-world thermostat, and the BOP test just pretend to be a virtual AC. Here the picture shows how the real work when I do the test. So now the next part is the results. Here we use binary cross entropy to train of the 3 models, and you can see after 100 epochs of the model exhibits stable convergence. And then because I mentioned before, if the quantization work with the pruning, maybe it can work best. So I pay more attention to it. So you can see this diagram shows almost all of the MLP successfully imitated the control behavior of the full MPC. And this diagram also shows that. So finally, we selected the small MLP with 90% pruning plus QAT. And here is the details. And here, this diagram shows another reason why we select the 90% pruning plus QAT model. Because you can say compared to other models, this model significantly smaller than others while maintaining competitive KPI. Here and here. And then for the system overhead, if you only calculate the model, the flash and the RAM usage is less than 1 kilobyte. That's very small. If you calculate the whole firmware, it's also very small. And in contrast, you can see if you want to run the full MPC, the RAM usage is much larger than the small MLP, and it's impossible to be deployed on the STM32. And here shows the detailed trade-off. So compared to full MPC, the small MP flash usage dramatically decrease, and the KPI control performance maintained. Here are the detailed outputs of the small MLP. And here the blue line shows that, and the yellow line is the full MPC. So you can see the control performance is very similar to each other. But you must notice that the AMPC controller operates as one shot server. It is running without receding horizon optimization. Of course, our research have some limitation because we only test it under the single zone. Thus, the original MP is small enough, and the training compression pipeline remains complex and labor intensive. So in my future work, I will develop AMPC for more complex case. For example, the multi-zone temperature control, and research how to realize plug and play. So in conclusion, this study presents any AMPC by distilling the complex mixed-integer MPC formulation into compact MP and applying load compression. We successfully address the computation bottlenecks. And in summary, the two-layer MLP with 90% pruning plus QAT emerge as the optimal solution. So thank you for your attention. That's all of my presentation.
Thank you, Huayu, and we will go to the Q&A session at the end of Jaap's presentation. So Jaap, could you please share your screen and start your talk?
Yes, I can. Give me a second.
We can see your screen and you can start, Jaap.
Yeah. Do you also see it full screen? I assume so, right? Okay.
Yes, we can see the full screen.
Okay, great. Thanks. So good afternoon or good morning, depending on who you are, where you are again. I'm Jaap, and I'm a second-year PhD student at KU Leuven and at Vito. And today I'd like to present my latest work in comparing white box and gray box MPC formulations on a Two-Zone BOPTEST case study. Basically, where MPC all starts, it's at the controller model. The controller model is basically a sort of digital twin of the building, which is a mathematical formulation that predicts how the temperature in the zones or the rooms of a building will evolve given how you steer your HVAC system or given the external influences like solar gains, occupancy, etc. Now, this control model can be used in an optimization problem given some constraints where you want to minimize a certain objective function. This objective function in buildings, it's mainly minimizing thermal discomfort and also energy use or CO2 emissions, etc. Now, this optimization problem, it takes a certain prediction horizon, so it looks into the future, which basically means that if you take into account predictions of your occupancy, of your external influences, together with the controller model that can predict how the temperature will behave, then you can basically take an optimal control action now, already taking into account the effects that it will have into the future. Now, this figure is missing something. We're now applying the control action at this moment to the real building, but we also need feedback from the real building to correctly initialize the next step. So we need to make use of some measurements, where most buildings usually only have a temperature sensor. So basically with that limited information, we have to update all the states of the control model, which in case of a white box model, those are quite some states. And that's where a state estimator comes in. What a state estimator basically does is, given limited information from the real building, it updates all the states of the control model while also taking into account the model mismatch between your controller model and your real building. Now, you can make a lot of different controller model types. On the one hand, you can go for a full white box or physics-based approach, where you really take into account all the physics and heat transfer phenomena of your heating system, but also your building envelope. On the other side of the spectrum, you can go to the black box approach, where you basically try to correlate input and outputs with each other with a generic structure like a neural network. Or you can do a hybrid approach, which is the gray box approach, where you start from limited physical equations and enrich them with data. And in buildings, these gray box models usually have the form of an RC model. Those are controller models. On the other hand, you also have a lot of state estimators that you can use. A state estimator, it basically determines the point where you start your next MPC iteration from. So it's both a controller model and the state estimator that will really determine the performance of the whole MPC. And with a lot of different types of controller models and state estimators, it's not always clear which combination or which prerequisites these models and state estimators must have to lead to efficient MPC, because you would only know that after you implement a specific combination in a real building and observing how it behaves. And that leads me to the research question I'm trying to answer today. I'm investigating this purely for white box and gray box controller models. How will I do this? I've evaluated and compared the MPC performance for a white box model and multiple RC models, so gray box models, all combined with different state estimators for a two-zone residential building case from BOPTEST, obviously. And this is where BOPTEST comes in. If we want to compare all these MPCs with different models, etc., then we need to do so based on the same boundary conditions. And obviously, I don't have to explain what BOPTEST is exactly, but I think you can also see the value in this framework for this research. As I said at the beginning of the presentation, I used the two-zone apartment use case. Before I did this work, I also did the same methodology for the best-stressed hydronic heat pump use case, which is a single zone. And this is a step up because these interzonal effects are more difficult to model, so that might cause some strain on the control models. So basically, what's happening here, we can control the set point, the temperature set point of the heat pump here, and the global mass flow that gets sent through both floor heating loops. We can also control the two valve positions such that we can distribute the mass flow to the two floor heating loops. Let's start with the gray box approach. So I already talked about RC models. What are they basically? They're simplified lumped capacity models that start from simpler heating dynamics from buildings. For example, in a regular building, you have through the windows, you have some solar radiation coming inside. You have your resistance to the outside, which due to heat conduction through the walls. And the room that you're sitting in has a certain capacity because it will not instantaneously fluctuate very largely. So we can express that in the form of a differential equation and then basically show that in the form of an RC model. Now the C and the R values, as well as the GA value in this case, those are trained with data because they are lumping a lot of different heat transfer phenomena together. So the types of RC models that we looked at in this case for only one zone is a first order, second order, and third order model. First order basically lumps every thermal mass into one capacitance and one resistance to the outside. The second order model adds a second state for the floor temperature because we have a floor heating loop. So then basically we're distinguishing between the time constants of the heat transfer due to the floor heating and the time constant of the zone. And similarly, when we can also move to a third order model where we make the same distinction between the time constant of the wall. Well, now these are for one of the two zones, as I said before. So in order to come up with the whole gray box model of the two-zone case, we have to connect two of these RC models together. And here I show an example of what such a, what it would look like if you connect two third-order models for that use case. It becomes already quite large. We basically connect it by adding a resistance between the two zone temperatures of both day and night zone. Now, how will we actually estimate these parameters? Because if you only have two data sets here, trying to estimate a lot of these parameters, that can become tricky for higher order models. So we basically perform a two-step approach. First, we estimate all the parameters of one zone while taking the other zone temperature as fixed. So in the first step, for example, for the day zone, you estimate the whole left half of this figure while taking the night zone temperature as a given, like the ambient. And if you do that for both zones separately, you use those parameters as an initial guess to perform an integrated fitting for all the parameters, but with tighter constraints on the parameters. And how will we do this mathematically? We can use the widely used least squares approximation, which basically minimizes the squared errors between measured and predicted temperatures. But we expect that mainly for lower order models that this formulation averages out dynamics that the model cannot explicitly take into account. And this is why we proposed a new least derivative squares formulation, where you also add another loss term specifically on the first derivative. And we think that this introduces an important bias such that the dynamics of these models are captured much better. I'll already show a first result here. So this is a comparison between the second order per zone RC model trained with the LS formulation, so least squares, and the LDS formulation. And you can see if you train the model with the first derivative included, it can capture the ripple effect much better as the ground truth, as you can see. The least squares, it may exhibit a lower average error, which is the green one, but you can see that the dynamics are really not captured well. And the hypothesis is in an MPC, if you use a good state estimator, this bias here will get corrected and you will have better MPC performance. But I'm getting ahead of myself. I'll show that later. The MPC, I'll keep it short here. We basically want to minimize the thermal energy use as well as penalize the thermal discomfort, which is modeled by the slack variables here. And of course, we're not trying to minimize the thermal energy use exactly, but rather the electricity use of the heat pump. So we will need to make, we made some additional bits to basically relate the control inputs that get fed into BOPTEST with the thermal energy, with the thermal power that we're minimizing in the MPC. So this is just to connect the necessary control actions with the things that we optimize into the RC model. So that was it for gray box. Now for white box, that's a whole other approach because we don't use the data that we emulate from BOPTEST. Rather, we use the technical information from the building envelope and from the HVAC system to construct a Modelica model, or Modelica optimization model purely from the ground up. And this optimization model should then be compatible with the tool Taco that we use. And what Taco basically does, I'll not discuss that in much detail here, but I would happily refer you to the paper of Taco, of which I can give you the DOI as well. But what Taco basically does is, as long as you have a twice differentiable controller model, it automatically translates that model into optimization code where it splits linear and nonlinear dynamics. And that operation has a lot of benefits for computation time while still preserving the model accuracy. And for the white box approach, because we really take the building envelope and HVAC system together, we can directly minimize the electric power of the heat pump. For the rest, the MPC optimization is all the same as the gray box approach. Regarding state estimation, that's the second major part, basically. We looked at two different state estimators. The first one is a stationary Kalman filter. And here I show you the more general equations of the time-varying Kalman filter. But basically, what a Kalman filter does is it updates all the states with only information from the measured ones, with a Kalman gain L. And that Kalman gain L is basically calculated by a trade-off between how accurate is your model prediction or how accurate is your measurement. Alternatively, we also developed a moving horizon estimation algorithm. And that's basically a whole other type of state estimator, because instead of working with matrices, you perform an optimization problem based on the past measurements. So basically, you're inferring a time series with your model dynamics based on a series of past measurements. And if you minimize the squared error between those, then you can estimate all the controller model states here at the time step that you needed, basically, while also enforcing the constraints, the same constraints as the MPC does. How will we validate our models? Because we also trained on the first derivatives, we can obviously validate based on the RMSE, which is a widely used metric. But we also want to see how well models track derivatives. And that's why we added also a formulation called the root mean squared derivative error, which is basically your RMSE on your first derivatives, which is noted here. And if we calculate that for all the models that we looked at, the ones with the green interior, those are the LDS gray box models. So with the first derivatives, the blue ones are the least squares gray box models, and the white box model shows up here. What we can basically see is moving from least squares to least derivative squares basically makes a trade-off between RMSE and RMSDE. So you're tracking your dynamics better at the cost of a slightly worse RMSE, which is reasonable because you're adding another term to your optimization. And you see that higher order gray box models are performing better. And also the white box model is performing better in terms of derivatives. Now the results for all the MPC formulations, I'll just give some MPC trajectories here because these are not all of them for visibility. And I only want to say here that you see that some formulations really don't do a good job. For example, the blue curve here, which in both day and night zone gives a lot of discomfort. But you do have formulations that are doing really good, like they're exploiting the flexibility of the building while exhibiting low energy use, like the orange one, if I'm correct. Yes. But a more complete picture is given on the next slide. So here I plotted in a scatter plot all the MPC KPIs from BOPTEST. On the x-axis, the thermal discomfort in Kelvin hours per week, and on the y-axis, the electricity use in kilowatt hours per square meters per week. And we can see some things in this graph. Firstly, both approaches, maybe I'll clarify first which points are what. The three upward pointing triangles below are all the white box MPCs. The green interior is a moving horizon estimator, blue interior is a Kalman filter, and a red interior doesn't use any state estimator. And the other shapes are increasing orders of RC models. So the first thing that we can see is that both approaches can lead to a decent MPC formulation if they use a proper state estimator. The white box approach is performing the best in this case, mainly when it's using the moving horizon estimator, but also the gray box approach here. If you compare it to the baseline rule-based controller here, then the thermal discomfort is being reduced drastically. The white box approach does outperform the gray box approach tremendously in terms of energy use. And we think that this is due to the controllability of the use case, and because the white box approach can really capture the HVAC system and the building envelope in one model. And then regarding the state estimators, a moving horizon estimator seems to outperform the Kalman filter for both approaches in this use case. So that's what I wanted to show in this presentation. And basically, we can now answer this the research question above, with that both approaches can lead to efficient MPCs when combined with a proper state estimator, and white box outperforms gray box in this case because of the complexity of the use case and because of its ability to model everything at once, basically. So thank you for your attention, and happy to answer any questions later in this webinar.
Thank you, Jaap, for this perfect and very informative presentation. Any question? I mean, for the audience, if you have any questions, you can type in the Q&A box, and I will speak loud. Maybe I can start to ask a few questions for Jaap. So my first question is for the Kalman filter. Basically, the AO matrix relies on the model, right?
The which matrix? The A matrix, you mean?
AO matrix. Like
the element, yes, yeah, the common gain, yes, exactly.
Yes. So for gray box model, this AO matrix, I think it's kind of easy. But for the purely white box model, how can you calculate the AO matrix?
Yeah, that's this is where the specific Taco implementation comes into play a bit. So indeed, you're right. For gray box, you basically have the data that you trained your models on. So you basically know the deviation of your real zone temperatures and your estimated zone temperatures. And then you can use these equations that I've shown on the slide a couple of times to calculate the P matrix and hence also the L matrix. For white box, that becomes difficult because Taco makes a distinction between linear and nonlinear dynamics. And what that means is not all dynamics are captured in its linear state space matrix, which is linearized around a certain working point. And that's why you cannot directly use the same equations as for gray box to come up with that P matrix and with the L matrix. So in this case, how I tackled that is I calculated P not as the estimation error covariance, but just as the covariance between the states. And I used that with some, I did that with some validation data of the white box model. That's not the best way to do it, but it's the best way that it is the best way that we can do it because of the specific Taco implementation. And that's also one of the reasons why the Kalman filter is outperformed by the moving horizon estimator.
For the moving horizon estimation, we also need to call the white box model, which I think is in Modelica, right? We need to call it like frequently.
Yeah, indeed. You need to every MPC step, every time step, you basically call it once you call the MPC and once you call the MHE. But that's mainly handled in the Taco environment, basically, because in Taco that optimization model is compiled and it's all the linearizations, etc. happen. But indeed, it's sorry.
It's compiled as a FMU.
Yes. Yeah.
Okay, I see. Any other questions from the audience? If not, maybe I'll ask one more question for Jaap. So currently you only consider temperature. So how about humidity? I think I'm not sure if Belgium maybe it's not so humid, but maybe in some parts of this world like China, Singapore, India, probably we need to consider humidity, right? So I think both for gray box model and the white box model, considering humidity would be very complicated, right?
Yeah, I agree. That's humidity also plays a role in the temperature itself, I think. And indeed, that's in the same reason you can also try to control the CO2 concentration, etc., which is also supported by BOPTEST. But here in my PhD and in this work, we we're only trying to do this analysis for temperature specifically. Yeah, maybe humidity can be a nice add-on, but yeah, I think the immediate next steps would be trying out more models, trying out more use cases, and really, yeah, grasp which model can lead to a good MPC performance with which state estimator for the low-hanging fruit, basically. So the models that everyone uses and the state estimators that are being widely used.
I see. Okay. My next question is also for Jaap. So for the state estimation, so why we need to do state estimation is there are some unmeasured states, right?
Sorry,
And
can you repeat that?
So the reason we need to do state estimation is in your MPC formulation there are some unmeasured states, and we need those unmeasured states as the initial value of your state transition function, right?
Yeah, exactly.
Okay, I see.
Yeah.
I got you. Yeah. I don't have any other questions for the audience. Do you have any other questions? If not, I think maybe we can stop early, but before we finish. So we would like to remind you, it's fine if you miss today's online talk. If you miss today's online talk, you can also go to this IBIPSA University YouTube channel to see to watch the recordings, which you can search IBIPSA University in YouTube. And we would also like to remind you there are some follow-up presentations organized by IBIPSA Education Committee. So you can scan the QR code to get the registration link, and this is a topic as well as the presenter as well as the time of the presentations. And the last but not least, we would ask for your support to be a supporting member, and your support is critical for us to continue those webinars and events. Yeah. So probably that's all for today. Pamela, are you still there?
I am, yes.
So maybe we can stop early today, maybe.
That's great. Thanks very much, everybody.